Yeah, so this is the streaming networks and streaming algorithms session. It's kind of a collection. I actually was the main person who tried to organize all the different sessions, and we started off with an initial sort of plan. You know, I mean, keynotes kind of defining the session, and as people come through, there's different time constraints and everything. So I think this is a pretty continuous section, but at the very end we'll also have a speaker from Netflix, which will be really interesting. But I don't know if it's exactly kind of related to streaming network algorithms. But anyways, so the first speaker that we have is David Bader. He's a professor of computing science and engineering at the College of Computing at Georgia Institute of Technology. He's the executive director of high performance and computing at Georgia Tech, and is also at the Center of Systems Biology there. He's a lead scientist of DARPA's ubiquitous high performance computing program, and is also the director of the Sony Toshiba IBM Center of Competence for the Cell Processor, which is also at Georgia Tech. So I'd like to let him take it.
Thanks. Can everyone hear me okay? Okay. Good. So thank you for inviting me to talk. And as I listened to the session yesterday, I realized that maybe my slides had too much lingo, so I went and I changed a lot of my slides. So bear with me, it's the first time I'm seeing them as well. I wanted to talk about opportunities and challenges in this interesting new space of big data or massive data-intensive computing. And my angle at coming at this is really from an algorithm designer, also from the high-performance computing community that traditionally has worked in big problems, grand challenges in scientific computing. Now, when I put together this talk, I wanted to first look at the big research agenda in this space. So what are the opportunities? And I thought about 5 areas that I think we really need to get through, driven by applications to solve a lot of these big data challenges. So I have the 5 summarized here, going from a new type of computing for the data analytics at hand, this notion of streaming that today's Tuesday session focuses on, visualization or InfoVis, different types of computing paradigms, heterogeneous systems, as well as energy efficiency. So I've broken down each of these 5, which I think are all going to be key, synergistically taken together to solve a lot of the big data challenges. Now, for each one of these, I have a slide. So the first opportunity deals with high-performance computing for massive graphs or massive data, if you will. And this is a theme throughout my talk this morning, where we have a lot of experience from computing for big problems, but primarily computing has developed for solving problems from computational spaces in physics, chemistry, mechanics, and so on, where the problems have been very regular. They often involve dense matrices or dense linear algebra. They're easy to partition to, say, clusters, and they involve a lot of floating point operations. But yet the problems that we see at hand today in big data, often we have to deal with new challenges, time-varying interactions among entities, different abstractions and relationships, very irregular traverses through data sets, and so on. And few computers today really run well on these problems. We've designed machines for a certain class of problem, and these are very different. So this will be a reoccurring theme. Second is the way we do computing has fundamentally changed. We still are in the mode of computing of what was done back decades ago, 50 years ago, with dusty decks, maybe in the 1960s, where we'd take our punch cards, we'd walk over to the machine would crunch a while, we'd get an answer out. So it was a very batch-oriented mode. But today, data is at motion, or we have to make real-time decisions very fast. And so we're getting into this new phase of bringing about streaming analytics. We have to look at tapping into data sources, maybe multiple data sources, and design systems, algorithms, machines, and even workflows for dealing with this very real issue of data in motion. Third is information visualization. We now have data sets where there are more entities in the data sets than pixels on our screen, or even pixels on the largest displays in national laboratories and industry. We have an example here of some social network-like graphs, and it's very easy for an analyst or a human to look at a small, simple graph. Maybe humans are good at looking at graphs with 100 people or objects in them, making some sense about it. But once you get into this big data realm, we get these fantastic hairballs or these explosions of information. It's very hard for any human to pick out patterns from those large data sets. And the fourth area that I want to focus on, again, this will be a theme throughout my talk, is the types of processing systems that we have for handling big data problems. Today, we often think of using CPUs, maybe they're multi-core. There are talks about using GPUs or graphics processors for doing some offloading when we have workflows that are very regular or can use vector operations. In fact, a lot of video processing can make efficient use of GPUs. Or if we have big data sets, we may go out to the cloud, or we may use MapReduce or Hadoop platform to solve those. There's also very special purpose machines. I have Cray on the lower right. I'll talk more about a machine that they have that's able to do very massive analytics, but with a very different architecture. And no one machine is perfect for every problem out there. What we need is a variety of platforms for different types of problems, and we have to have a very good ecosystem to tie those together. In fact, what we really need to do is look at heterogeneous platforms or architectures where we get the best of all breeds and are able to, for instance, glue together a Hadoop MapReduce cluster with maybe GPUs or a many-core Intel processor. So I think this is a very rich paradigm, or sorry, this is a very rich space for looking at future research, especially how to program this type of framework easily. If I have information sitting out on disk and I want to use Hadoop for part of it and then program with CUDA on a GPU, well, that's apples and oranges. I want a unified framework to be able to move between those different types of compute platforms. And the last opportunity is very important, not just for high-performance computing, but all computing, where energy is now a limiting factor. One of the limiting factors, we go out to massive data centers because we can leverage their scale and get cheaper performance or cheaper cost for performance on a big data center. And the amount of energy that we can bring into a facility is often measured in terms of megawatts, the same amount of power that powers moderate-sized cities in the US. And so everything that we do, we now have to start thinking about not just time to compute, but how many joules are we spending. So this is being driven from the top down from high-performance computing, but even from the bottom up of computing, when we have smartphones, we have batteries, and we're looking at extending battery life, we're also having the same constraint. So from the top and bottom, we're being pushed by energy, and we have to start thinking about designing algorithms with energy as a first principle. In this space of big data, moving data often is one of the major costs of energy in any system. So we have to think about efficiently processing on data streams and data sets where they reside without having to move them around. So these are big opportunities. I think these are 5 grand challenges that we have for the next 5 to 10 years. Now my motivation, my research, I have a slide that gives an overview, and then I'll go into some technical details. We try in my lab to solve exascale streaming data analytics. These are real-world challenges, and they come from a variety of domains. So for instance, in healthcare, we may be looking at disease spread, detection and prevention of epidemics and pandemics, or in massive social networks that are ubiquitous today, we're trying to understand communities, interactions between those communities, emerging trends. And this even spills over into other application areas like transportation or evacuation during a storm or a crisis. What do people do? How do they interact? How do they move? Or social change, if we want behaviors to change to make, for instance, a smart power grid operate better, we have to understand social networks. In intelligence, there are a lot of business analytics, marketing, fraud detection, security, and so on that involve massive data sets. Systems biology, the electric power grid. We work on a project with Pacific Northwest National Lab on how to make the US power grid more resilient to failure. And power is very important for communication, transportation, energy, water, the food supply. We have to know that we have resilient power. And finally, modeling and simulation, being able to perform full-scale economic, social, political simulations of whole nations really, again, is an exascale streaming data problem. The types of questions that we want to ask on these data sets are often enormous. So for instance, we want to operate on social networks where there are billions of entities. And you could think about those entities as maybe vertices in a graph, and interactions between them are edges of different types. We may want to find allegiance switching, someone who goes from one committee to another. We may want to understand community detection and community structure. We want to look at when new committees form, when other committees dissipate, and so on. Or we may be looking for phase changes. When do the network structure, when does the network structure have some significant change and transform from one to another? So these are different types of queries that I have on our slide that are representative of the types of things that we may want to do with this abstraction. So during this talk, I'll mention a lot about social networks, but understand that this paradigm or this abstraction with graphs or social networks can apply to a number of important domains. We also have the availability of massive data today, and so I'm probably preaching to the choir here about data sources, but regularly from finance to social networks to science and so on, there are data sources on the order of petabytes and more where there are megabytes to, terabytes or more of daily updates that we need to understand and process. And we also have an added problem of sensor fusion. We have all of these data sources, and at the end of the day, many of the applications I talk about really are ones where we need to make real-time decisions based on these data sets. And there may be no right or wrong answer, but we have to make the best decision at hand to protect populations, to understand when a fraud is happening within a business, and so on. So we have to do the best that we can. I work on a number of DARPA projects that were mentioned in the introduction, and these represent the new phase of computing where we're really interested in streaming performance on big data sets. One project where I'm the applications lead is with NVIDIA, the GPU company, and we are looking at a problem of taking a massive supercomputer, a traditional supercomputer, and trying to shrink it down into the size of a single rack, which is about the size of a large refrigerator in your house. It uses more energy, about 57 kilowatts. And that's taking something today that uses megawatts, maybe 10 to 20 megawatts, and shrinking it down into a kilowatt, which is what we normally would have in a high-end machine room, to create a computer that could be deployed on a number of different platforms, the back of a Humvee, in a UAV, and so on, or in a machine room on a college campus. And that machine has to be easy to program, resilient to attack, and also very energy efficient, which is one of the primary design points. We're looking at new applications to drive the design of this machine. As I mentioned, I'm the applications lead, and we're looking at streaming sensor problems and also streaming graph problems to have, for the first time, a parallel machine that is purpose-built to handle streaming analytics versus batch processing in a traditional machine room. What's neat about this machine, you can see it from the title down here, is that the organization of the machine is totally different. This isn't a cluster with GPUs accelerating it, but a brand new design where the memory subsystem is configurable by the application programmer. So if you like a lot of deep memory hierarchy and caches, you can configure the machine one way. If you like scratch pad memories, if you want some memory shared and some memory private, and so on, you have the ability to reconfigure the memory hierarchy on the fly. We're also part of other national centers that look at big data problems. For instance, the Center for Adaptive Supercomputing Software for Multivariate Architectures CASMT for short, is led by Pacific Northwest National Lab, and we're a task lead at looking at massive social networks on this project. We're applying it to problems found in internet security, computational biology, and I already mentioned power grid stability, where we're investigating new architectures and new algorithms to be able to work on these large-scale problems. And I'll have more slides today of work that has been sponsored by this center. As one example, back in September 2009, my students decided that they're going to play on Twitter without telling me, which is really what this work is. But in fact, we decided that we would take a full collection of Twitter, just public tweets, the same tweets that go into the Library of Congress, and take a massive data feed over several months. And in fact, September and October 2009, which resulted in terabytes of information. We funneled it down into a special supercomputer that was able to do big scale analytics very fast. This is a Cray XMT or multi-threaded processor, as I'll talk about in a few slides. And we ran a very compute-intensive kernel called between centrality that looks at vertices in the graph that have some importance to them or some influence in the network. And so in this study, it was really a proof of concept that we could take a massive information stream and make decisions on the fly. And we looked at two events that occurred in fall of 2009. One was the H1N1 scare. How many of you remember H1N1? It was this big scare. There's thought out there that maybe it would kill off double-digit percentages of the population or of the world. It was spreading. We didn't know how bad it would be, and we didn't have any inoculations available at the time. And the second event up here was a 500-year flood event in Atlanta. And I think since 2009, we've had about 2 more 500-year flood events, so it's maybe not as interesting. But what we're trying to do is figure out, could we identify tweeters that were very influential, keeping the population safe from these events, that weren't your commercial media outlets, but were really news sources, very good news sources that were influencing a big community, but we couldn't really pick them out beforehand. So I'll just pick one of these 2 events and tell you a little bit more. For instance, H1N1. On the results here, we have the 15 top influencers using some computationally intensive social networking algorithms on about 4 terabytes of information. We got this ranked list of the top 15 influencers. And on here we see government sources. Number 1 is CDC flu, so anecdotally our methods are doing well. We see number 4 is flu.gov, the New York Times, CNN, Time, Magazine, and so on. So those are commercial news sources that you expect to influence a large part of the population. But the one that's really interesting is number 3 on this list, official PACs. How many of you have heard of PACs? Does anyone know what it is?
Penny Arcade? Is it Penny Arcade?
So what is Penny Arcade?
That's a big trade show that they put on twice a year.
So I know PACs only from my students. Political action? No. So it turned out it's a bunch of gamers. And these gamers were in Seattle. And no stereotypes, but there was a bunch of young boys. And they all got H1N1. And they started tweeting about, what are the symptoms? What is it like? Did you die yet? How bad is it? How sick do you get? And it turned out to be a big nothing. H1N1 was a scare that nothing really resulted. But it turned out that they were very influential. They were really the first group that started tweeting and were very influential on how people got their information as a primary source. So what we'd like to be able to do is plug in a system like this real time into data sources and be able to get good information to keep populations safe. And we don't always know who's going to be the influential news source before it happens. Often it's a non-commercial news source where we get a lot of good information. We've also applied social networking problems, I mentioned, to the US power grid, to proteomic problems. For time, I'll skip over a lot of these slides. And also, these are 2 figures coming from social network analysis. the bottom figure is from communications of the ACM, looking at subgraph isomorphism, or having a pattern that you're trying to detect in a larger graph. These are problems that relate to intelligence, surveillance, and others. Also has a big use for this type of analysis. But I'm going to focus on graphs, and graphs are really pervasive in large-scale data analysis. We saw yesterday a number of problems from astrophysics. Josh Bloom had a great talk of looking for outliers and anomalies in big data sets, where we're often looking at clustering problems, matching problems, and so on. In bioinformatics, there's a lot of work now on looking at identifying drug targets and different pathways where we may be applying algorithms related to centrality and clustering. And then from social informatics that I'll talk about more today, we're trying to discover, for instance, emergent communities, looking at the spread of information, as I had in my earlier slide, where our graph problems that we're trying to solve often relate to clustering, but we may look for things like shortest paths, flows through networks, and so on. So these are very different domains, but more and more we have data sets that represent interactions and time-varying interactions between entities, and that's what we'd like to make sense of. So I'm going to take a little detour. My background is in high-performance computing, and I've been in that community for many decades at this point. And for those of you who aren't familiar with this community, it really arose to solve some of the grand challenge problems in physics and chemistry, and we've gone around a pattern of having applications, real-world applications that we'd like to solve. And that was a big set of applications. We were very eager to solve these problems. And we would then build architectures that worked very well on those problems. Often the architectures focused on putting the investment into the processor design for floating point, for a very tight integration among nearest neighbor communication of those processors. We had essentially massively regular architectures. And then our programming models, we moved into more of a canonical approach of doing message passing. MPI is the message passing interface that worked very well for many of these problems that had nearest neighbor communication or very regular grids that we could tile up and give to each processor. And then we would evaluate the machines that we were building with a benchmark that's been around for quite some time called Top 500 that lists the 500 fastest or most capable supercomputers in the world. The list is released twice a year, and it measures computers on a synthetic benchmark of solving a system of dense matrices, essentially solving a system of dense linear algebra. And then we've gone around this sort of flywheel many, many times till today we have what we consider supercomputers, but we've sort of painted ourselves into a corner, and we've taken the applications that we want to solve that have natural concurrency and filtered down into the set of applications that we say are parallel or parallelizable because our mindset has changed. But this is the first time in decades that we can really rethink computer architecture. We see this proliferation of new types of computing. We have map-reduced clusters, we have GPU, we have multi-core, many-core CPUs, and we can now rethink the way we do architecture for solving the problems that we originally wanted to solve, the real-world applications, not just the one that run well on today's machines. So this is sort of a word of caution that I have, that in the high-performance computing or scientific computing community, we equated for many years scientific computing with using a particular paradigm like MPI. And that was great. We had some fantastic insights for numerous problems in chemistry and physics and fluid dynamics and others. But other applications that didn't match that paradigm were impossible to solve efficiently, and we kind of left by the wayside. So for our big data community, we have to rethink, and right now we have Hadoop and MapReduce, which may be great for some analyses, but we have to keep our mind broad about the possibilities that we have at hand. It's such a rich time for looking at architectures and platforms that we have to make sure that we don't go in a single direction, but really form an ecosystem of platforms. in the big data space, I have just sort of a cartoon of the wide variety of architectures available, and it has to do with where we place data within the system and how we query the data. So on the left-hand side, we have big external disk-like systems. So a Hadoop instance programmed with MapReduce may be one example of this. There's traditional databases that may be a mix of in-memory and out-of-memory processing. Cloud or cluster, however you define it, is here. But also there are platforms with very large shared memories where all of the data may sit within internal memory. This isn't that far-fetched. There are machines that we can acquire today that have terabytes of main memory, and if a problem fits in there, it may be a more feasible or efficient way to compute on a problem where we have to have decisions made in real time than going out to external disk. So for instance, ease of programming, maybe Hadoop is easier, arguably easier than programming in C or with CUDA for doing things in memory. Maybe not. But for performance and energy, we're often pushed towards doing things on the right-hand side because the closer our application is to our memory subsystem and our processors, the less power we're expending to drive pins or to spin disks or even use solid-state disks. So if we're looking at performance and energy, we'll get a much higher performance as we go to the right of this slide versus the left. In fact, I don't have a slide on it, but I can share some results where we're able to use a large shared memory system and solve a problem in the order of minutes that takes about 3 weeks to solve with Hadoop MapReduce. And so we're looking at doing things on the order of cycles versus tens of thousands of cycles to access memory between the two extremes on this slide. So if I look at the graph analysis that I talked about earlier, we want to place requirements on the architectures that we need, and the applications are often dominated not by the compute or the floating point operations, but by the memory operations. So latency to go out to addresses. I'm at a graph, I want to look at a adjacent vertex, and I have to traverse across an edge, and I need to pull something into my processor which looks like a random access where I don't know a priori where it's going to be across a global address space. I may have many of these at once. I'm traversing through a graph and I hit a vertex that has many neighbors. I want to pull them all in at once to look at that community. And I essentially have no computation that I can use to hide or account for that memory latency. Often in scientific computing, I may have a lot of work I can do, maybe local FFTs or some sort of matrix operation or vector operation that I can be operating as I'm getting my next data set. But here we typically don't have that. And our access pattern we can't predict beforehand, so prefetching is unlikely to help. In fact, it may hurt us. And we may be pulling in big cache lines, maybe 128 bytes, when we want just a word out of it. So we're chewing up our memory bandwidth for moving a big unit of information when we're only accessing bits and pieces of it. That also is a big place where power is spent, pulling in memory to the processor and pulling in big cache lines when they're not needed. So we have potentially abysmal locality at all levels of the memory hierarchy. What we want is a machine that has a very large memory capacity. We want to take our problem and just throw it out into memory. We don't want to worry about partitioning it. We don't want to worry about some of the problems that I had down here, looking at mapping from local to remote or global numbering. We don't want to replicate parts of the graph and deal with sort of ghosted cells on processors and beyond. What we'd like to have is a low latency, high bandwidth for small messages. We want some latency tolerant automatically in the machine so that as we're going out to memory to get our information, we're able to not have our machine look like it's at a halt or a stopping point as we're waiting the tens or hundreds to thousands of cycles for that information. And also we want lightweight synchronization mechanisms. When I'm accessing a graph, I may want to lock some vertices so I can update them, or I want to insert an edge into a graph or delete an edge out of the graph. And I don't want to trap up to the operating system and wait what's an eternity in computing time to make those updates. I'd like in a single cycle to be able to modify a data structure without worrying about concurrency issues with other threads. Now, there are new benchmarks out there that are starting to look at influencing the design of machines for these types of properties. One benchmark here is Graph 500, and it's a list that's released twice a year at the same time as the top 500 benchmark. And it's had 3 releases so far. The next release will be in June in Germany. And you can find it by going to graph500.org. On the last list, there's about 50 machines on the list. So it's a growing effort. And there's now procurements, federal procurements that are using this benchmark. So it's gained some traction. And it's really trying to address 5 science areas or application areas, from security, medical informatics, social networks, data enrichment, to symbolic networks such as simulating neurons in a brain. And the graph, or the benchmark, creates a big synthetic graph and then tries to do operations on that graph, like searching within that graph. So arguably it's a simplistic benchmark, but what it's looking at is the time to traverse edges in a graph in the benchmark. So it's more looking at memory performance for big data problems than looking at floating point performance in the microprocessor. So bandwidth is important, memory subsystem design is important. From a prior release of the benchmark, these are some of the top results. And the performance now is given in a canonic measure called TEPS, which stands for traversed edges per second. You see it on the right-hand side. Size is log base 2 of the size of the graph that we're generating. So size 30 is 1 billion vertices, size 31 is 2 billion vertices in the graph, and then there's a fixed number of edges that are 16 times the number of vertices. The generator of the graph is a model of a social network, and a traversal is done on this graph to try to search the vertices. Future kernels will add single source shortest paths and other community detection algorithms into the benchmark. You see a number of supercomputers on here. For instance, Blue Gene Q from IBM. This is a machine at Lawrence Berkeley National Lab from Cray, XE6, a very traditional machine. And those are really like taking a sledgehammer to the problem. It's big iron, and it's able to solve some very large problems and do incredibly well. But there's also smaller systems. This is one machine at Georgia Tech from Intel, which has 40 physical cores, 80 logical cores, and on the order of a terabyte of memory, and it's able to do very well on a single platform, 5 billion edges traversed per second. And then there's some other machines, like Convey is a new HPC startup that's using FPGAs in a very interesting system design. This is a machine at Sandia National Laboratories and is getting quite an incredible performance for a single socket. So often your problems may require a supercomputer and may require the memory of a very large system on here. You'll want one of those. But if your problem is small enough, you'll probably want to find the machine that best suits your problem size. And this benchmark is now influencing many of those system designs. One of the machines on that list is this Cray XMT. And this is a newer machine. In fact, at the bottom of the slide, the XMT2 was just released. The Swiss have bought one that's available to the scientific community. And it has 512 processors and can go up to 64 terabytes of main shared memory. So this is a game changer type of machine that's purpose-built to run these types of data analytics and graph problems. Each processor is a custom ASIC called ThreadStorm that replaces the x86 class processor in Cray's traditional line of machines. The processor is a unique design with hardware threads. It has no caches whatsoever, since caches hinder the performance when you have no locality in your problem. There's single cycle context switch to a 128 hardware context. You can have multiple outstanding memory references, and this is how you get latency tolerance. When you go to access memory and you're waiting for it to come back, you switch to another thread. And as long as you have an application with enough concurrency, you're able to have the illusion of fulfilling your memory request one per cycle. There's also support for fine-grained word-level synchronization. Every word of memory has a couple special bits. One of them is called a full empty bit, where on a single cycle I can have producer-consumer relationships between a process that is writing information and others that wish to consume it. So this machine is really a workhorse, and it works well on these big data type problems, graph analytics. If I have a problem with a lot of locality or a very regular operation that runs well on my traditional cluster, I won't use this machine. It'll work like a dog. But if I have one without locality, where I really have all of these irregular accesses, then it's amazing. Recently, maybe last month, Cray announced an appliance called UARC Data and a framework for doing essentially a single board of this machine as an appliance for some big data problems. So you may see more about this and more adoption. I also mentioned Intel has some platforms in multi-core and many-core, and we get some great performance on graph algorithms using a multi-socket Intel machine. And right now we have some platforms that have up to 2 terabytes of main memory. So instead of fighting with Hadoop and MapReduce or fighting with message passing or clusters, if you can just take your problem and drop it in this unstructured space into memory, often that's a big win, both in terms of programming, but also cost. For the sake of time, I think I'm going to skip through some of these slides. I want to move into now massive streaming graph analysis. So this is the switching gears to the heart of our research. Now that I've given you a lot of motivation, we often have users like, this is user A, and she's logged into, say, Facebook, and she pokes user B at time 1. Well, he's sitting out there, he's on Facebook too, he gets the poke. Maybe she goes off and she sends user C a message. He pokes her back, and it goes on. They have some activities on Facebook, and I could start to represent their actions in terms of a graph where the nouns in the system, the people, fan pages, events are all vertices in the graph, and their actions are now different types of edges. So a poke may be a type of message or an edge. A message, a private message, visiting someone's wall, clicking on a link, etc. Every one of those actions generates an edge. And this is true for many types of online activities and social networks, and it produces a big stream of billions or trillions of edges in real time that we want to be able to make sense of and understand for many of the reasons I gave earlier in this talk. In fact, we have a project with DARPA under the ADAMS program, Anomaly Detection at Multiple Scales, where we're looking at host-based monitoring of full organizations where everyone is agreeable to being monitored, and we're looking for insider threats within organizations where we can understand the actions a user takes on their computer, such as logging on and off, clicking on files or links, sharing files, plugging in USB keys, etc. We can essentially create an abstraction or a graph out of that. We want to do the same sorts of things of understanding patterns over time and also anomalies within those streams. So you can imagine that we abstract away this problem into really a large set of edges. There's no beginning or end. We just want to be able to tap into a stream and then make decisions on the fly. So here I've just pictured canonically a Cray supercomputer, and instead of seeing the domain, it sees this graph abstraction with vertices and edges, maybe colored in different ways for the different types of vertices and edges. And it represents the information from the domain. And then we have a group of analysts who are really the humans in the loop that have to make decisions about what to do, whether it's on a battlefield or whether it's a security unit of a company. Maybe they're tracking disease spread at the CDC. They may have a question that they want to ask. So question 1, an analyst has, and they'll represent it in terms of a Sparkle query or some other type of query language into that abstraction of the graph, and they'll hope to get their answer. And notice that in this scenario, they're asking a question at the same time that this machine is always constantly building a view of the world in terms of a big graph. And maybe it's not just one question, but maybe there's multiple questions that need to be answered when this analyst has a question, or maybe there are persistent queries that exist over longer periods of time. So this is the workflow or the scenario that we have for the types of applications we're developing. The last part of my talk has some of our research results, and I just have a few slides on each. But we've spent a lot of time to come up with a strawman data structure that we call STINGER. And STINGER stands for Spatio-Temporal Interaction Networks and Graphs Extensible Representation. It's also the mascot at Georgia Tech, so we like Sting, and that worked out well. Thank God for graduate students who like acronyms and coming up with names for them. And then we have some streaming updates to a few analytics, such as tracking clustering coefficients in a graph, looking at connected components, updating between centrality. And these are just representative of some types of social networking analysis algorithms, often that are thought of only in the static domain. Given a fixed graph, can you compute these? But now we're trying to do updates to the graph, maybe track important actors like this between centrality, may give me anecdotally a ranked list of influencers in the network. And instead of recomputing every time we get a new edge, we would like to have a big win by having maybe in constant time or some very low polynomial time updates where we can figure out this edge changes things or it doesn't, rather than doing a full recompute each step. So this data structure that we have called Stinger is actually now in use in a number of other frameworks out there. It's not the best or optimized, but it gives us a way to reason about algorithms because we have an implementation we can play with. And there are a number of collaborators on designing this data structure and representation so that it works well with some existing applications. The basic operations in the data structure are being able to insert and update edges and also delete both vertices and edges. This is interesting because most of the time when we think about graphs or we represent them maybe as sparse matrices, our vertex set is often fixed. In these problems, our vertex set may change over time as we're running, and what we want are analytics that are able to account for that, give us meaningful answers, be able to make decisions, but not crash when an edge or a vertex is deleted underneath us. We want to be able to remove old edges, maybe by timestamp or by importance, because in steady state, if I'm plugging into a data stream, maybe I can do that for a day, a month, a year, but after some point in time, I've filled up my memory with edges, and I'm going to need to be able to delete something for every new piece of information I put in. We haven't really faced that yet, but that's going to become a very important issue because no matter what system we have, we're going to fill it up. And then finally, we need to have some way of checkpointing what we're doing. This is a picture of the data structure. I won't go into a lot of details, but essentially we have ways to apply concurrency either across the vertices or across units of the edges. We also have a way to filter edges by type efficiently, so a user may be able to see all edges that are red or blue, but not green edges. And we need to be able to give that illusion. Or queries may come in that ask about, give me the number of connected components, considering only the purple and black edges, but not the yellow or green edges. And so we want to be able to, on the fly, view the graph with a particular filter and very efficiently solve those types of queries. Our goal is to then have streaming graph analytics where we're operating on, say, billions of vertices, trillions of edges, and maybe handling millions of updates per second. So this is really a goal. And our challenge is to be able to run different types of analytics, for instance, community detection, connected components, clustering, etc., and be able to do it in the face of all of these updates. Now, if I didn't care about processing those updates, I would be able to just rerun and make decisions later, but I want to be able to keep up with these streams, these very high rate streams, and that's where the challenge occurs. So I want to design algorithms, and once I have the algorithm, it dictates what speed I'll be able to keep up with for ingesting new data. So in clustering coefficients, this is really a count of a ratio of triples that I have in a graph, where a triple is looking at this vertex V. I have a closed triple with I and J because the three edges in that triangle exist. With M and N, I have an open triple because I have an edge from V to M and a V to M, but I'm missing the edge from M to N. So clustering coefficient is an analytic that's often used to look at the strength of a community within a social network. This is, you may like it, you may not like it, but this is an analytic that a lot of analysts do use. And the clustering coefficient is then just a ratio of the number of closed triples, like the green one on the left, divided by all triples of the vertices in the graph. So we can locally count the number of triangles around each vertex, and then globally count those across the entire graph. And we know that we may triple count some triangles, so we have to divide out that double counting. So what we'd like to be able to do is track clustering coefficients over time. And what that means is after we have an initial count, we want to look at inserting and deleting edges from this graph and being able to maintain the clustering coefficient counts. So we need a fast way to deal with inserts and deletes. We have a paper from 2 years ago that's able to do this. And just to cut to the chase, the performance we have on the right-hand side of this figure, an exact way to keep track where we're able to handle about 50,000 updates per second to an approximate method that's able to handle about 200,000 updates per second. And by approximate, it means that usually we have a correct answer, but we recognize that there's a lot of noise in these data sets, so what does it mean to have an exact answer anyway? If we can do very good, that's what this approximate algorithm is able to do. And we have batch sizes, so here we're batching 4,000 edges together that we process instead of just handling the problem edge by edge, which is batch size 1, where we really have no speed up or no capability. So the larger batches really aren't that important. If I have 200,000 edges per second and I'm batching them up 4,000 at a time, I'm able to make sort of sub-second decisions, if you will. Often an analyst needs to make decisions every minute or every 5 minutes, so I can really batch up and do this as a batch problem. In the area of connected components, I may want to track connected components in a streaming graph. So why would I want to do this? In many of my social networks, I have a big, giant connected components and just little crud around it. So what sense does it make? Well, I may want to find a small community that never attaches to the big community, but stays active and around over long periods of time. That's an anomaly I'll want to look at it. Or I want to see if some community that was part of the big collective for some reason breaks off. I want to understand what happened. I want to look for big phase changes in community structure and so on. So this is often a very hard problem to do, to find connected components in a big social network that aren't the major component. What we're able to do is both insert and delete edges and be able to keep up with fast streams. This is some results on that Cray XMT machine that I talked about. I don't have time to go through all of the results, but on the right-hand side we have a larger graph, and we have a couple results. The x-axis is essentially the block size of updates that we're using the batch size. The y-axis is a log scale of updates per second, so higher is better. And we have a couple results going from static recompute, which is the slowest down here, and on the top is just, if we imagine we only have insert edges only. Inserts are easy to track connected components. It's basically like a union find where all you can do is join if the two endpoints are in different components. If they're in the same component, that edge didn't change your connected components. Deletes make it much harder, and so the triangles, if you will, are handling deletes as well. And we have a neat little trick that looks for a spanning tree, and you can decide whether or not a deleted edge is within the backbone spanning tree or not. So it's a little trick. We published this last year on this performance of tracking connected components over time. And we also have results of tracking between centrality, and the measure of between centrality is looking at the number of shortest paths in a graph that go through a particular vertex divided by the total number of shortest paths. And again, we have some results that are newly available where we're able to track the important actors, if you will, in networks. And there's a number of collaboration networks, publication and citation networks, and so on, where people are very interested in looking at who's the most influential over time. And so we're able to get good speed ups on problems like this. I won't go through all the performance numbers, but this has been a very rich area. And I think looking at streaming algorithms, there's a lot of challenges and work to be done. For instance, if we just think very simply, we can take single-shot graph analysis algorithms, the type we teach to undergrads, looking for shortest paths, looking for connected components, and extend it in the temporal domain where we're looking for that feature either at an interval of time or at a unit of time. There's a second temporal domain where we may be looking at change detection of a particular feature. Tell me anytime a shortest path got dramatically shorter, for instance. But where we're focused right now is this third, truly dynamic, truly fully temporal analytic that has no static analog. For instance, tell me anytime a small committee stays independent versus merges with a larger group. Or when does a vertex jump between communities? We don't even have a catalog for these types of analytics on streaming data, streaming graphs. And so that's where we're focused. There's a lot of other open questions out there for massive data analytics. How do we diagnose the health of a streaming system versus having a sensor that shut down on us? What are the new analytics? How do we scale up from thousands and millions to billions? How do we model these data streams? Are the algorithms resilient to noise? For instance, many algorithms out there are accurate within 1 in a million, and if you have an anomaly of your algorithm, it gives you a false answer. A human is pretty good at detecting 1 in a million when your data set only has 10,000 items. But when you're dealing with trillions, an error rate of 1 in a million, you'll be inundated with false positives, and that will overload a human. How do I visualize these types of graphs? What accelerators help me? How do I use GPUs? How do I use different architectures efficiently, like MapReduce clouds, the massively multi-thread architectures that I mentioned? This is a huge, huge space to figure out how we should move forward. So to conclude, I want to thank Jason Reedy, my research scientist, a number of graduate students from my lab, some who've graduated and gone on to bigger, better places, and we have a lot of collaborations with Pacific Northwest National Lab and others. So they're really the workhorse, but behind the work here, we have a number of publications on our website that you're free to take a look at. All of the code that I mentioned is freely available as open source from my website. And then we have a lot of support coming from federal agencies, national labs, and also corporate sponsors. So thank you very much. I hope that gives you some food for thought for today's streaming analytics, and I'll take any questions. Thank you.
It would seem like these tools would be great to study language, the evolution and structure of language in general, and things like who wrote Shakespeare and a visual thesaurus is really good. Is work being done along those lines?
So absolutely, that's a fascinating question, linguistics and study of language. In fact, I didn't talk about it here, but I have a $1 million NSF PETA Apps Award looking at computational phylogeny, looking at evolutionary histories of genomes. And that work and algorithms come from the linguistics committee of tracking languages or looking at evolution of documents. So that has a lot of relationship to what I talked about here. Unfortunately, for time, I didn't present any of that, but that's a very, very good connection. And the problems have very similar properties of what I mentioned here.
I enjoyed your talk a lot. Thanks.
Thank you.
I grew up about 5 minutes from Georgia Tech, so welcome to California. So as you mentioned, Sparkle, do you see that as a viable long-term sort of query mechanism for this type of data? Is that going to get better, or is something else going to be invented to?
So the question was a bit about Sparkle, and right now it's being used. There was a workshop that we co-held with Pacific Northwest National Labs and many of these big data spaces to identify what are reasonable Sparkle queries, because that's what's being used right now in a lot of industry and a lot of laboratories to do these big data queries. So I think in the future, we're going to have to look more broadly, maybe domain-specific languages or others that are able to take into account the different types of platforms that we have. But for today, if we can accelerate Sparkle queries, we're helping a very large community that already exists.
So I was looking at your the section where you're talking about kind of computing the clustering coefficients, and I quickly was scanning the paper that you mentioned, and one of the things you use is loop filters to estimate these, to make these counts locally. And I was curious, so in the theory community, in theory CS, people have been looking at exact approximation algorithms for computing clustering coefficients on these streaming graphs. And of course, we can prove various bounds about what you can do, how well you can approximate, but you actually have a system which is computing this, and you have some implicit approximations using your loop filters. Do you find that the level of approximation you get from your system is acceptable, or do you think there's room for more theory in terms of proving guarantees on what you can do?
So first, thank you for those comments. We did use a Bloom filter for inserts. It doesn't work well for deletes. And what I'd say is there's a rich area of theory, but yet what we talk about as online algorithms or streaming algorithms are often different from theory's view of it. So in the theory community, often a streaming graph is you have a fixed set of edges, and you can make a constant or a small polynomial number passes over the edge set, and what can you say either exactly or approximately about that graph and its properties? Versus here, we have an infinite stream of edges, we want to tap in, and then make decisions. So at the end of the day, I think, first of all, yes, the theory committee can have what we need are new models for reasoning about these, new ways of handling noise in the data. What does it mean to have an approximation? What are acceptable levels of false positive, false negatives? What is the accuracy of the methods as I scale up, not from tens or thousands, but to billions and trillions, which makes a real difference in practice. At the for all of these types of problems that I mentioned, we have a human who has to make a decision, and they have to make the best decision possible. So the theory is fantastic, but every 5 minutes someone's got to make a decision, and we have to get to the point where that theory can help them with that process to know what's the best decision at any moment of time, what should they be doing. So I think, in short, yes, the theory committee can contribute significantly to this area. Thank you. Computing has fundamentally changed. We still are in the mode of computing of what was done back decades ago, 50 years ago, with dusty decks, maybe in the 1960s, where we'd take our punch cards, we'd walk over to the machine would crunch a while, we'd get an answer out. So it was a very batch-oriented mode, but today data is at motion, or we have to make real-time decisions very fast. And so we're getting into this new phase of worrying about streaming analytics. We have to look at tapping into data sources, maybe multiple data sources, and design systems, algorithms, machines, and even workflows for dealing with this very real issue of data in motion. Third is information visualization. We now have data sets where there are more entities in the data sets than pixels on our screen, or even pixels on the largest displays in national laboratories and industry. We have an example here of some social network-like graphs, and it's very easy for an analyst or a human to look at a small, simple graph. Maybe humans are good at looking at graphs with 100 people or objects in them, making some sense about it. But once you get into this big data realm, we get these fantastic hairballs, or these, as well as energy efficiency. So I've broken down each of these 5, which I think are all going to be key, synergistically taken together to solve a lot of the big data challenges. Now, for each one of these, I have a slide. So the first opportunity deals with high-performance computing for massive graphs or massive data, if you will. And this is a theme throughout my talk this morning, where we have a lot of experience from computing for big problems, but primarily computing has developed for solving problems from computational spaces in physics, chemistry, mechanics, and so on, where the problems have been very regular. They often involve dense matrices or dense linear algebra. They're easy to partition to, say, clusters, and they involve a lot of floating point operations. But yet the problems that we see at hand today in big data, often we have to deal with new challenges, time-varying interactions among entities, different abstractions and relationships, very irregular traverses through data sets, and so on. And few computers today really run well on these problems. We've designed machines for a certain class of problem, and these are very different. So this will be a reoccurring theme. Second is the way we do.
Yeah, so this is the streaming networks and streaming algorithms session. It's kind of a collection. I actually was the main person who tried to organize all the different sessions, and we started off with an initial sort of plan, you know, I mean, the keynotes kind of defined the session, and as people come through, there's different time constraints and everything, so I think this is a pretty continuous section, but at the very end we'll also have a speaker from Netflix, which will be really interesting, but I don't know if it's exactly kind of related to streaming network algorithms. But anyways, so the first speaker that we have is David Bader. He's a professor of computing science and engineering at the College of Computing at Georgia Institute of Technology. He's the executive director of high performance and computing at Georgia Tech, and is also at the Center of Systems Biology there. He's a lead scientist of DARPA's ubiquitous high performance computing program, and is also the director of the Sony Toshiba IBM Center of Competence for the Cell Processor, which is also at Georgia Tech. So I'd like to let him take it.
Thanks. Can everyone hear me okay? Okay. Good. So thank you for inviting me to talk. And as I listened to the session yesterday, I realized that maybe my slides had too much lingo, so I went and I changed a lot of my slides. So bear with me, it's the first time I'm seeing them as well. I wanted to talk about opportunities and challenges in this interesting new space of big data or massive data-intensive computing. And my angle at coming at this is really from an algorithm designer, also from the high-performance computing community that traditionally has worked in big problems, grand challenges in scientific computing. Now, when I put together this talk, I wanted to first look at the big research agenda in this space. So what are the opportunities? And I thought about 5 areas that I think we really need to get through, driven by applications to solve a lot of these big data challenges. So I have the 5 summarized here, going from a new type of computing for the data analytics at hand, this notion of streaming that today's Tuesday session focuses on, visualization or InfoVis, different types of computing paradigms, heterogeneous systems, explosions of information. It's very hard for any human to pick out patterns from those large data sets. And the fourth area that I want to focus on, again, this will be a theme throughout my talk, is the types of processing systems that we have for handling big data problems. Today, we often think of using CPUs, maybe they're multi-core. There are talks about using GPUs or graphics processors for doing some offloading when we have workflows that are very regular or can use vector operations. In fact, a lot of video processing can make efficient use of GPUs. Or if we have big data sets, we may go out to the cloud, or we may use MapReduce or Hadoop platform to solve those. There's also very special purpose machines. I have Cray on the lower right. I'll talk more about a machine that they have that's able to do very massive analytics, but with a very different architecture. And no one machine is perfect for every problem out there. What we need is a variety of platforms for different types of problems, and we have to have a very good ecosystem to tie those together. In fact, what we really need to do is look at heterogeneous platforms or architectures where we get the best of all breeds and are able to, for instance, glue together a Hadoop MapReduce cluster